So in the last video, we already looked at some of the rules related to uncertainties that we should know how to use. And now we're going to go ahead and look at some more of these rules. And basically all the rules will be covered in this video, and we'll also be doing a small example just to look at all of these in action. So the third rule for uncertainties is this, that when quantities are multiplied or divided. So again, we know both of these basically mean the same thing. So when quantities are either multiplied or divided, I'm writing this here, they're fractional, and by the same principle, their percentage uncertainties are added. So when quantities were being added and subtracted, in that case the absolute uncertainties were added. When quantities are being multiplied or divided, their fractional or the percentage uncertainties are added. It doesn't mean that you have to work with both of these. Sometimes, and this is most of the times, that you are given the percentage uncertainties, you will work with that. But that same thing, for example, if it's up to you, then you could also choose to do the same thing with fractional uncertainties, right? Again, we'll see all of these in action in the example that follows. In addition, let's say there's a formula in which quantities are also being multiplied or divided, but additionally, one of those quantities is also raised to a certain power. So for that, what's the rule in? So when a quantity is raised to a power, again, the fractional or the percentage uncertainty here is multiplied by that power. Right, so that's the next rule. And a lot of the times in actual exam questions, you will mostly have to use 3 and 4 together to solve problems. And the fifth one is more so regarding the representation of uncertainties. And basically when you've done the entire problem and you have values with yourself, how do you then represent these properly? So the idea is this, that the absolute uncertainty is written to 1 SF, right, to one significant figure. And then the principal value is written to the same number of SF, not to the same number of SF, I would say to the same number of decimal places as the absolute uncertainty. Right, so once you'll have the absolute uncertainty, you also have the principal value. So you write the absolute uncertainty to 1 SF, and whatever number of decimal places that is, you write the principal value to the same number of decimal places. Now let's do an example to see how this works out. So example 1, and we'll see all of the 3 rules above in action here. So we are talking about a cylinder, and for the cylinder we know that the volume formula, this is also something you're supposed to know, that's pi r square h or pi r square L. If the diameter is given to u, which is basically what will be given in this case, you can write the radius as half of the diameter squared L, and basically expanding, you see that this is going to be pi d square L over 4. And here both of these are given to you. So L is given as this, R is given as this. So L is 7.6 plus or minus 0.1 centimeters, and you're not provided R, instead you're provided with D. So D is given as 2.5 plus or minus 0.1 centimeters, right? So you can choose to do this, and there's no compulsion on how to do this. I just like to find out the principal value first and then do all of the calculations for uncertainties. So first I'm just trying to find out the actual volume, and for that I'll just need to plug in the actual values. So this is going to be pi and there's this d which is 2.5 squared, L is 7.6, all of this divided by 4. Because my dimensions were also in centimeters, the volume would also be in centimeter cubed, and this turns out to be 37.31. Intentionally I'm writing this to a greater accuracy because I don't know what my uncertainty is going to be like, and I need to round this later as well. So this is my volume. Now if I look at the formula, I can see that pi by 4 is again a constant, and the quantities which are being multiplied or divided are basically these, d and L, and there's also a square on the d. So without any square, I would just say this, that the percentage uncertainty in V would be the percentage uncertainty in D plus the percentage uncertainty in L. But because of that power 2, this is basically rule number 4 in action, that the uncertainty, the percentage uncertainty, would be multiplied by the power on that variable. And now I need to find out the percentage uncertainties. This is not very difficult. For D, I know this is the absolute, this is the, the principal value. So I can write this as 0.1 over 2.5. And again, it's up to you. You can also choose to work with fractional uncertainties. There's no such compulsion here. So 0.1 over 2.5 times 100 to make this percentage. These brackets then close. And now for the percentage uncertainty of L would be 0.1 over 7.6 times 100. My question to you guys, would my uncertainty, would this calculation be different if, let's say for example, instead of the diameter, if I had radius in this equation, if I use this form? And the answer is no, because we know that if something is multiplied or divided by a constant, the percentage uncertainty does not change. So when you work this out, this turns out to be 9.31%. This is the percentage uncertainty. So to find the actual absolute uncertainty, you'll just take this percentage of the actual value. So 9.31% of that 37.31. This was 9.32 actually, and this turns out to be 3.48. Now we'll see rule number 5 in action, which is to how to represent these quantities actually. So I know that if I'm talking about the volume, I write this as the principal value plus or minus delta V. So here I'm going to write this as my actual value, which was 37.31 plus or minus 3.48. Now the rule goes like this, that you first write this to 1 SF. So reading from the left, the first non-zero figure is an SF, and every number after, regardless of whether it's a 0 or not, that is also an SF. So first SF, second SF, is this value 5 or something more? The answer is no. So this is just going to become plus or minus 3. So this is basically written to the units place. Hence this value must then also be written to the units place. So for the units place, I look at the next one. Again, it's not more than or equal to 5. So this would just become 37 plus or minus 3. And along with the unit, I'm going to write this as cm cube. So this is what my final answer looks like. Let's do another one. So example number 2. The relationship given in this case is this. And you are given these quantities along with their absolute uncertainties. So you're given G and L. So G is 9.7 plus or minus 0.6 meter per second square, and L is 0.55 plus or minus 0.2 meters. And the question says find T along with its absolute uncertainty. Just looking at the formula, you can see that things are being multiplied or divided, plus all of that power stuff. So you know you cannot get the absolute uncertainty directly. You'll have to go through the path of the percentage uncertainty, find those, and then do what we just did to find the absolute uncertainty. Another thing that you must have also noted here is we need to find the uncertainty in T, but right now G is the subject of the equation. Let's go ahead and change that. So this would become t square equals 4 pi square L over G, and then taking the square root gives me this. So this would become 2 pi root L over G. And this is the formula that I'm now going to use. And now again, as we did previously, let's first try to find out the actual principal value. So for t naught, I would just substitute my values, 2 pi root L over G, so 0.55 over 9.7, and this would give you the actual value of the time period, which turns out to be 1.496. Again, I'm keeping this to a greater accuracy. I don't know what my uncertainty is going to be like. And then I see that the time period is 2 pi, and again these are the two variables which are being multiplied or divided, and there's a square root on top. The square root can basically be treated as a power half. We've talked about this before as well. So when I'm talking about the percentage uncertainty in t, I can say this is half, because this is half on both of them. Half the percentage uncertainty in L plus half of the percentage uncertainty in G. I've just factored out that half is common. And now I need to find the percentage uncertainties again. So for L, it's going to be 0.2 over 0.55. So half is there for everything. 0.2 over 0.55. This would be times 100 plus 0.6 over 9.7. And this would also be times 100, because I see this happening twice. I can also factor out the 100 as common. And using this, I get a percentage uncertainty value for t. And this turns out to be 4.91%. Now again, for the absolute uncertainty value, I'll take this percentage of the actual principal value, which was 1.496, and this turns out to be 0.0734. Now again, writing down the final thing. So t would be the actual value, which is 1.496 plus or minus 0.0734. Again, the steps are the same. First, write the absolute uncertainty to 1 SF. So that's just going to be 0.07, because not an SF, not an SF, first SF, second SF, not greater than or equal to 5. So that's how it remains. And this is 2 decimal place, so my value should also be written to 2 decimal place. So 1, 2, this is more than or equal to 5. So this would become 1.50 plus or minus 0.07, and the units outside, and this is my final answer. Alright, so these are a few examples on how you can tackle questions, and in the following videos you will see actual past paper questions solved in the exact same way. So see you there.